Interaction Design Styles, From Mouse Gestures to Direct Manipulation, Part 3. Narrated by Lydia Ngami. Here is an overview of this lesson. Mouse gestures are a way of converting a continuous motion of the pointing device into a specific command, much like drawing a symbol in the air to signal an action. When a gesture is recognized, the system triggers the appropriate function without the user having to click a menu item. Pie menus enhance this concept by displaying a circular menu that appears at the cursor location, giving immediate visual feedback about possible actions. The combination of gesture detection and pie menu feedback creates a fluid, almost instinctive interaction, especially for power users who want to keep their hands on the mouse. In practice, developers have built these capabilities as extensions for the Mozilla family of browsers, allowing users to navigate, bookmark, or close tabs with a swipe or a circular motion. The result is a faster workflow, but it also demands that users learn a set of consistent gestures. The Optimos project was a research effort that built upon the basic idea of mouse gestures by adding a full suite of pie menus to the Mozilla browser ecosystem. Researchers designed a set of gestures that could be performed with a single mouse stroke, and each gesture would summon a context-sensitive pie menu showing the most relevant commands. For example, drawing a clockwise circle over a link would bring up options to open, bookmark, or share that link. By providing visual cues at the moment of gesture completion, Optimos reduced the cognitive load associated with remembering abstract shortcuts. User studies reported a measurable decrease in task completion time, especially for navigation-heavy tasks such as browsing multiple tabs. The project demonstrated that when gestures are coupled with clear visual feedback, the interaction becomes both powerful and learnable. A question-and-answer dialogue, often called a wizard, guides users through a multi-step process by asking one question at a time. Each subsequent question can depend on the answer given previously, allowing the system to adapt the flow dynamically. This style is familiar from everyday devices such as bank ATMs, where the machine asks for a PIN, then the amount, then confirms the transaction. In desktop software, wizards appear during installations, configuration, or complex tasks like setting up a new email account. The advantage of this approach is that it reduces the need for users to understand the entire process up front. They can focus on one decision at a time. However, experienced users may find wizards tedious because they force a linear path even when the user already knows the desired outcome. Wizards excel at providing a structured pathway for users who are unfamiliar with a task, ensuring that no critical step is missed. By presenting only the necessary fields at each stage, they keep the interface uncluttered and reduce the chance of error. This guided approach also allows developers to embed help text and validation directly next to each input, improving data quality. On the downside, the same linear progression can become a bottleneck for power users who prefer to jump directly to the final configuration. Because the wizard forces a sequential order, users cannot skip ahead or backtrack without using the provided navigation buttons, which can feel restrictive. Designers must therefore balance the need for guidance with shortcuts, such as offering an advanced mode that bypasses the wizard entirely. FormFill is perhaps the most ubiquitous interaction style on both desktop and web platforms. It mimics the familiar experience of filling out a paper form where each piece of information is entered into a designated field. Users type their name, address, or other data into text boxes, select options from drop-down lists, or check boxes to indicate preferences. Because the layout is static, the user can see all required fields at once, which helps them plan the order of entry. This style is especially common in office suites, database frontends, and e-commerce sites where customer details must be captured. While simple, the effectiveness of a form depends heavily on its design, including clarity of layout, field labeling, and assistance mechanisms. When designing a form, the first priority is a clear visual layout that groups related fields together and aligns labels consistently. Users should be able to instantly recognize what type of data each field expects, whether it is a date, a numeric value, or free text. Providing concise help text next to each field can prevent misunderstandings and reduce validation errors. Automatic advancement, often implemented as tabbing, allows the cursor to move to the next logical field after the user presses enter, speeding up data entry. However, this feature must respect the natural order of the form to avoid confusion. A well-placed cancel button lets users abort the process without losing partially entered data, while an undo or edit function lets them correct mistakes. Pre-filled fields, such as a known address or default country, can save time, and list boxes give users a controlled set of options, minimizing free-form entry errors. Spreadsheets extend the form fill concept by arranging fields in a two-dimensional grid, allowing users to enter large amounts of data quickly. Each cell can be thought of as an individual input field, and rows often represent records while columns represent attributes. Because spreadsheets support copy and paste formulas, then data validation, they are ideal for tasks like bulk order entry or financial reporting. The visual similarity to a table makes it easy for users to scan for missing values or inconsistencies. Nevertheless, the flexibility of spreadsheets can also lead to errors if users inadvertently overwrite formulas or enter data in the wrong column. Good spreadsheet design includes locked cells, drop-down lists, and conditional formatting to guide correct entry. The first core feature of direct manipulation is the visibility of the objects that matter to the user. Everything they need to act upon is displayed on the screen. Second, actions are incremental and provide continuous feedback, so the user can see the effect of each small step before committing to the final result. Third, operations are reversible, meaning that users can undo or backtrack with a simple gesture like dragging an object back to its original position. These characteristics combine to create an environment where users feel in control, can experiment safely, and can quickly correct mistakes. For instance, when resizing a rectangle in a graphics editor, the user drags a corner and sees the shape change in real time, and can release the mouse button when satisfied or pull back to shrink it again. Ben Schneiderman identified several psychological benefits that arise from direct manipulation interfaces. Novice users can grasp basic functionality quickly because the actions map directly onto visible objects, eliminating the need to memorize complex command syntax. As users perform actions, they receive immediate visual confirmation that their goals are being advanced, reinforcing a sense of progress. The reversible nature of the interactions reduces anxiety. Users know they can undo a mistake, which makes the system feel more forgiving. Over time, this leads to greater confidence, as users develop an intuition for how the system will respond to their inputs. These factors together contribute to a more enjoyable and productive user experience. Direct manipulation is evident in many everyday applications. File managers such as Windows Explorer let users drag files into folders, copy them, or delete them by moving them to a trash icon. Graphics programs like Photoshop allow artists to reshape layers, adjust colors, and apply filters by interacting directly with the canvas. Video games often rely on direct manipulation for character movement, object interaction, and inventory management, creating immersive experiences. Even critical industrial control systems use direct manipulation. Operators can click on a schematic to zoom into a sensor, drag a valve icon to open or close it, and receive instant visual alerts when conditions deviate from normal. In each case, the interface mirrors a physical action, making the system more understandable under pressure. While direct manipulation thrives on the desktop, implementing it on web pages has historically been challenging due to the constraints of HTML, CSS, and JavaScript. Early browsers lacked the ability to capture fine-grained mouse movements or render complex graphics without external plugins. As a result, developers turned to technologies like Flash and Java applets to provide rich, interactive experiences that could support drag-and-drop, real-time drawing, or game mechanics. Today, modern web standards such as HTML5 Canvas and WebGL have reduced the need for plugins, allowing native direct manipulation in browsers. Nevertheless, many web applications still rely on simpler interactions, and designers must weigh performance, accessibility, and cross-browser compatibility when deciding how much direct manipulation to incorporate. In human-computer interaction theory, the gulf of execution refers to the difficulty of translating a user's intention into system actions, while the gulf of evaluation concerns interpreting the system's response. Direct manipulation helps narrow both gulfs by presenting actions that closely resemble the user's mental model and by delivering instant visual feedback. When a user drags a slider to adjust volume, they see the change reflected immediately, allowing them to evaluate whether the outcome matches their expectation. This tight feedback loop encourages iterative refinement. The user can make small adjustments, observe the result, and continue until satisfaction is achieved. Consequently, tasks become more efficient, error rates drop, and users feel more in control of the interaction.